For this lesson, we're going to be taking a look at the intersection of straight lines, so the intersection of lines in R3 in 3 dimensions. In order to discuss that, the first thing you need to do is remember this is something you've done before, which is the intersections of lines in R2. And that was probably introduced to you in your grade 10 course as systems of linear equations. When we have two lines in R2, and these things can all be applied to more than two lines. In theory, you can have any number of lines where you come up with one of these three possible options. But it's easier to focus on two lines. There are three possible outcomes for that situation. The situation that we normally expect to see, simply because mathematically this is usually the most interesting one, is two lines that intersect at a point. And that's the one solution case. Then we have a situation where there's no solution, and that can occur if the lines are parallel to each other and they don't touch each other. So they are parallel but distinct. And then finally we have infinite solutions, and that is also parallel lines. The difference is those lines are coincident with each other, meaning they are the same line. So one solution, we have two lines and they cross at a point. When we do the algebra for that, the algebra just tends to make sense. It's what we expect. We get an x coordinate, we get a y coordinate, and that x and y coordinate together represents the coordinates of the point. No solution, that's an easy enough one to visualize. I draw two parallel lines. They're never going to touch each other. Algebraically, the result is usually something strange. I'm writing it as the simplest possible version of that result, which is something like 0 equals 1. But any other impossible result would also be fine here. For example, 1 equals 2 or 5 equals 1,000. We're basically getting a result that is never true. And then the flip side of that one is infinite solutions. And algebraically, that's actually the easier one to get your head wrapped around, which is you get a result that's always true. For example, you get a result like 3 equals 3 or 0 equals 0 or 1 equals 1. But the diagram is harder to do, and this is the best I could do with the technology I had available. I started with two lines, and you can see there's a blue dotted line in there and there's a red dotted line in there, and they are overlapping each other and they're the same line. And so that means there are an infinite number of points of intersection. Extending what we know from R2 to R3, we actually end up with a very similar set of conditions. First of all, we do end up with those same three possible outcomes. It's just what those outcomes mean is a little bit more complicated now in 3 dimensions. If we get one unique solution, now this is far less likely to occur in R3 than it is in R2. In R2, if you just throw down two random straight lines, you actually have to be pretty careful if you want those lines to be parallel. Most lines are not parallel, which means most lines are actually going to have one solution. In R3, that's actually not so common, and that's because of three-dimensional space. There are many, many more lines that don't intersect than do intersect. But sometimes we do get a situation where the lines intersect at a single point, and since we can represent these lines as vectors, we can actually find the angle between those two lines. We can use we can use the dot product and cosine of theta from the direction vectors to find that angle. The most common situation in R3 is actually this second one, no solution. And what I've got in blue here is actually the most common one of those. Actually, I'm sorry. No, the one in red is the more common of the two. So first of all, let's talk about what each one means. So your first option is the lines do not intersect. And the reason for that is that the lines are parallel and distinct. So essentially that means you've got two parallel lines like we had in R2. And if we have two parallel lines, they have to lie on the same plane. Or you can make a plane that both of those lines lie on. So that's what we're talking about here, in the same plane. The more common of the two scenarios is this one, which is the idea of skew lines. The lines are not parallel, their direction vectors are not collinear, but they don't intersect because they lie in different planes. R3 is really big, and there are lots of different ways that you can orient lines in R3 so that they won't intersect with each other. And there are many, many ways to set up skew lines that don't intersect. And as a matter of fact, if you just thought about all of the infinite number of possible lines, most of them are going to fall into this category. They're going to be skew lines that do not intersect. And then finally, you can skip over this B part. We already talked about that. Finally, we've got infinite solutions, and that's actually quite simple again. That is, the two lines are coincident. Now, a linear system, introducing some new terminology, we talk about a system that is consistent or inconsistent. If the system has at least one solution or infinite solutions, then it's a consistent system, and that means it gets a result that's permitted. An inconsistent system will still get a result like what we saw before, 0 equals 1. That's an inconsistent solution. Or you'll find some numbers that work, and then you'll try to do a verification, a left side, right side, and you'll get an inconsistency between your left side and right side in one of your equations. Now, before we go on to some exercises, just a quick recap. When we look in R2, we've got a couple of forms of the equation of a line that should already be very familiar to us from when we first started examining straight lines. I'm not going to do any examples from this category because you've done these for years. We also have these new versions of equations for lines. And when we talk about vector and parametric, those are really the same thing. They're just different forms. The parametric equations come from breaking the vector equation into its components. That's all it is. So you can work backwards and forwards between these quite easily. In R3, we have those vector equations, we have those parametric equations, and then we also introduced another type called a symmetric equation of a line in R3. And the one thing I think I'll just point out here is that the direction vector from the symmetric equation, we actually get that from these values, A, B, and C. That's the direction vector of this line. And then x naught, y naught, and z naught, those are the coordinates of the point that the initial position vector points to. If you need to, you can go back and review these particular lessons. I just wanted to remind you of those. Okay, so let's start off with, and I'm not going to spend a lot of time on these examples. I'm not doing any examples from R2. I'm just going to go to R3. Solve the following systems. So I've got a couple we're going to do. We'll start with part A and describe the geometric relationship between the lines. So what kind of solution or what kind of outcome do we have? In this case, I've got the vector r1 and the vector r2. r1 is defined as an initial position vector and a direction vector. r2 is an initial position vector and a direction vector. It is almost always a good idea to break these into their parametric form. So for the vector r1, I actually end up with x1 or x. Let's just write it as x because I'll explain that in a moment. X is equal to -2 plus t times 5. So actually let me write that as 5t. Y is equal to 0 plus t. And z is equal to -3 plus 3t. And here I should have mentioned that t is a member of R and s is a member of R. Those are the scale factors for the direction vectors. For the vector r2, I end up with the x coordinate is equal to 5 minus s. The y coordinate is equal to 8 plus 2s. And the z coordinate is equal to -6 minus 3s. And now that I have these systems of equations, or now that I have these parametric equations, I can start to put these together to find a system of equations. Now, the one thing I want to point out to you is that the x, y, and z, those represent the various x, y, and z coordinates, or the points on R1 and the points on R2. If we are trying to solve the following system, we're trying to find out where these points are equal to each other. And so that was why I didn't write this as x1, well, I could have. I could have done that. And then, in order to solve, what I need to do is I need to set x1 to x2. And I need to set y1 to y2. And I need to set z1 to z2. And this is why it didn't really matter that I wrote that, because I actually end up with these equations. Negative 2 plus 5t is equal to 5 minus s. And that's going to be equation number 1. Then for the y coordinates, I end up with t is equal to 8 plus 2s. Call that equation 2. And then for the z, I end up with negative 3 plus 3t is equal to negative 6 minus 3s, and call that equation number 3. And how about I do a better job of writing the number 3? It's not my fault. It's the edge of the screen. Okay, so I've got my 3 equations. As you can see, I only have 2 unknowns. I've got t and s. So with 3 equations and 2 unknowns, generally I'm going to focus on 2 of my equations, and then I'm going to have to do a left side, right side check to verify the third one. So when I take a look here, if you're someone who likes to do substitution, it seems pretty obvious that you would use equation 2 and you would substitute it in. I'm a fan of elimination, and so in that case, I think what I'm going to do when I look at these, I see a negative s here and positive 2s there. So I think what I can do is I'm going to take equation number 1 and I'm going to multiply it by 2. So that gives me negative 4 plus 10t. That's the left side times 2. And the right side times 2 becomes 10 minus 2s. Yes, I could have brought my constants all together, but it didn't really matter. I'll do that in a moment. I'm going to add these together to get rid of my s's. And so I end up with negative 4 plus 11t is equal to 18, and that's going to be 0s, so that's now gone. And then I end up with 11t is equal to 22, so the numbers work out quite nicely here. And I end up with t is simply equal to 2. Now that is what I got from combining equations 1 and 2. I can now, and I really strongly recommend this, you don't want to lose track of things, I'm now going to sub t equal 2 into one of these 2 equations. So I'm going to sub t equal 2 into, and in this case I'll choose equation 2. So I end up with 2 equals 8 plus 2s, and I end up with negative 6 equals 2s, or s is equal to negative 3. And because I've done it this way, I've worked exclusively between equations 1 and 2, and so now all I need to do is go verify using equation 3. And so my left side of equation 3 is equal to negative 3 plus 3t, which is negative 3 plus 3 times 2, which is equal to negative 3 plus 6, which is equal to 3. My right side of equation 3 is negative 6 minus 3s, which is negative 6 minus 3 times negative 3, which is negative 6 plus 9, which is equal to 3. So my left side is equal to right side, and since I got my solution from equations 1 and 2, and I have verified it with equation 3, so therefore the system is consistent. There's that word we introduced for describing these, and we have a solution is a point, or a point of intersection, and I really should figure out what that point is. So the way I figure out that point is I actually take my t equal 2 and my s equal negative 3, and I sub that into either one of these sets. So let's do that. We'll just go ahead and do that kind of on the fly. And I think the easier one to work with here is t equal 2. So if I sub in 2 for each of these, then here I'm going to get 5 times 2 is 10. So that becomes an 8. And that becomes a 2. And then 3 times 2 is 6. Minus 3 is 3. So 8, 2, 3 is my solution. So that I'm going to come down here. 8, 2, 3. And if I went through that a little too quickly, you could go ahead and write that out yourself. And you could also try it with s, and you would find you get the same result. Okay, for this next one, I'm giving you the equation in symmetric form. And so the first thing, again, as I mentioned, parametric form is the way to go when you're solving these. So option 1, which I'm going to call your kind of your brute force option, in that we would convert to parametric and then we would solve. And that is a perfectly fine way to do this. But there actually is a second option available to us here, which is to recall that in symmetric form, the denominators, and just to remind you, the denominator of this one would be 1. The denominators of these fractions represent the direction vectors. So if we call this one line 1 and we call this one line 2, then that means my direction vector for line 1 is simply equal to 3, 4, 6. And my direction vector for line 2 is equal to 1/2, 2/3, and 1. Now you may look at this quite reasonably and say, so what? And if you look at that and you say, so what, then you should go with method 1. You should convert these to parametric equations and you should solve them. But if you look, obviously I'm trying to get somewhere with this, so if you look a little more closely, then you might ask yourself, or forget about looking closely, why am I going through this? What would be the value of this? This would only have value if these two direction vectors were collinear. So I'm actually seeing something here that makes me think these lines might be parallel. So what does it mean for these to be collinear? Well, that would occur if d1 is equal to some scale factor times d2. Is that the case? Well, that would be true if 3 was equal to k times 1/2, if 4 was equal to k times 2/3, and if 6 was equal to k times 1. And now this one immediately gives me k is equal to 6. And then I just do a left side, right side here. Left side is equal to 3. Right side is equal to 6 times 1/2, which is 3. Oh, that one worked. Left side is equal to 4. And right side is equal to 6 times 2/3, which is 6 divided by 3 is 2, and that's equal to 4. And that one works. Or you could just solve each of these for k individually. But as it turns out, they are collinear. And if they're collinear, that means I only have two options for these lines. So since we have discovered that these lines are collinear, we've only got two options here, which means we can have no solution or we can have infinite solutions. The idea of a single solution is now off the table. Now, how do we distinguish between those two possibilities? Well, the other thing I want to point out to you about equations in symmetric form is that this also gives you the initial position vector, which is a way of saying it tells us a point that's on the line. These equations would be infinite if, since they're already parallel, if this point, or if the point represented here lies on this line, or if the point represented here lies on this line, then that means that they would be collinear. So what is the point? Let's actually pull that off of here. So what point does this one represent? So this represents, if we call this line 1, then that would mean that, let's call it point 1, is going to be -4, +12, 3. Or I could look at point 2, which would be from this one, that would be 0, 10, and -5. So I know this point is on line 1. Can I show it's on line 2? Or I know that this point is on line 2. Can I show that it's on line 1? And if I can do either of those two things, then I know that this is going to work out. That would mean that these are the same. Now the way to do that, again, it's this idea of consistent versus inconsistent. I think what I need to do is take a copy of what I've got here. Let's see. Actually, let's just copy all of this that I've done. Okay, so what I'm going to do is I'm going to test, let's see, I'm going to test the point, well, it looks like P2 is actually easier. So I'm going to test the point P2, which is 0, 10, -5. But if I'm going to test that, then I have to test it on L1. So what I'm going to do is I'm going to look at x plus 4 over 3, which is equal to, and I sub in my 0 plus 4 over 3, so I end up with 4/3. Now, these symmetric equations rely on all of these pieces being the same. So now let's test the middle part, y minus 12 over 4. That becomes 10 minus 12 over 4, which is -2 over 4, which is -1/2. We've already got an inconsistency. And just for the sake of completeness, let's look at z minus 3 over 6, which becomes -5 minus 3 over 6, which becomes -8 over 6, which is -4/3. And so since my results are inconsistent, what's my conclusion? Therefore, P2 is not on L1, therefore there is no solution. And that means the lines are parallel but distinct, which means they're parallel but they're not actually touching. They don't lie on top of each other. So there's a couple of examples. I didn't do an example for infinite solutions just because those are actually, mathematically we can throw them in there, but that's an exceedingly rare situation normally, and it's also the least interesting one because your system of equations very quickly falls into, you just end up with consistent results and you end up with something like 1 equals 1 or 0 equals 0. Okay, so that's it. There is your assigned work. There's more here from this chapter if you want to look it up, or if you're having some difficulty with this and you need to review some stuff from R2 in particular, you can go back to some of the earlier questions in this chapter. But these 4 questions really hit upon the key that I want you to practice on this particular lesson.